All right, yeah, so 1.3 is the next section. This is limits at infinity. We've already talked about infinite limits. All right, just showing off. Good thing I have the insurance and the case on my iPad. All right, so limits at infinity is different from infinite limits, okay? So let's come over here on this little side and we'll talk about, first of all, infinite limits are going to be something like the limit as x goes to 3 from the left-hand side of f of x equals infinity, right? That is an infinite limit. The limit is infinity. And so what's the consequence of that? What do we know about the graph of f of x then at x equals 3 based on that? Yeah, the consequence is so f has a vertical asymptote at x equals 3. Okay, so that's an infinite limit when the y values increase or decrease without bound. What we're doing now is we're talking about limits at infinity. And so what that is that's one of two types of limits. That's the limit as x goes to infinity or the limit as x goes to negative infinity. Okay, so these by definition are one-sided limits, right? They're one-sided limits. You can only approach positive infinity from which side? The left side, right? If you were on your way to positive infinity and you met a guy coming the other way, whoa, right? Like, how'd you get over there? Right? So these are one-sided limits. When we analyze the y values for huge values of positive or negative x, we are analyzing the what of the graph? The end behavior. Yeah. And so we had this discussion in pre-cal. There's really only a few things a function can do at its end, way down the line to the right or way down the line to the left, if it exists at all, okay? Let's list some of the possibilities here. Let's just draw them. As we go up to the right, the y values can do this, right? The y values can still go to infinity. So we can have an infinite limit at infinity. As x gets really big, y gets really big. What else could happen? As you go out to the right, the y values could go to negative infinity. Now, if that's the case, we wouldn't say there's a vertical asymptote there because it's not happening at a specific value of x. This is happening as we go out to the right. Forever and ever and ever, the y values increase by bound, kind of like x squared or negative x squared. So that would be kind of interesting. It could be like the natural log of x where maybe there's not even a graph there, so it really even wouldn't be worth talking about it. When we talk about the end behavior of a graph, we're not talking about its end, but we're talking about positive or negative infinity. So what are some other things it could do? Well, the graph of sine and cosine, what do they do forever and ever as x goes to infinity? They oscillate between two fixed values. So you can have something like that, in which case, what do you think the limit would be? We'll talk about that. If it oscillates between two fixed values as you go out forever and ever and ever, the limit's going to fail to exist. So the ones that we're actually more interested possibly are the ones that, that start tapering off and approach, hey, Learning to Lead committee. Anyone want to join that? It's in the recording now. Oh, really? It quit unexpectedly. Okay. I'll reopen it. That's a great committee, by the way. It's always good to lead, but first you must learn to lead. All right? Yeah, okay. And you could put that on your high school transcript, right? I learned to lead, and then I led. And then you can kind of set yourself apart from other people who maybe learned to lead, but then never had the opportunity to lead, or who led without learning, you know. So anyway, that was just background talk while I tried to restart this. Anyway, so that's on the recording. So if you want more information, just rewind and listen again. Okay. So we're going to be interested in the ones that taper off towards some specific y value. And they could do it like that, or let me use a different flavor. They could actually do it like this. Okay? They can actually kind of oscillate by less and less, in which case they're going to approach some finite y value, which we'll call y equals L. And of course, you probably already know that if that's the case, what graphical manifestation appears? Yeah, a horizontal asymptote, okay, which I call an HA. Now, a horizontal asymptote is, in fact, an asymptote, but it is not a discontinuity, okay? It does not interrupt the flow of the graph. The only asymptote that is a discontinuity is the vertical asymptote because it runs north and south, and you can't get through it without lifting your pencil. But a horizontal asymptote does not break the flow of the graph. You can run alongside it forever and ever without lifting your pen or pencil, or you can even cross a horizontal asymptote infinitely many times. Okay, you can't cross the vertical asymptote. So let's go ahead and we'll summarize that here in a little bit. Let's evaluate the following limits without a calculator using our knowledge of pre-cal or algebra 2. So first thing you want to know is the limit as x goes to infinity. So that's an end behavior limit. And which end is that analyzing, left or right? Yeah, that's looking at the right end behavior of the graph. So we have local behavior, which is all the cool stuff like the local max, local mins, vertical asymptotes, very exciting in quotations. And then we have the end behavior, which is really kind of boring. It's going to just be one of these few things up here. All right, so what do you know about this function? This is a polynomial, right? And it belongs to the quintic family, right? So if you think about it, for huge values of x, no, bigger than that even, which term contributes predominantly to the bulk of the growth of the problem? Yeah, the largest exponent. We call that the leading term, right? So this is what's kind of cool about limits at infinity. You can kind of forsake a lot of the other stuff that's, you know, increasingly insignificant as x gets bigger and bigger, and focus on the one piece in each portion of the function that's causing the majority of the growth. You can't do that for local behavior, okay? So here's what we could do. Spot the largest term and just say everything else behind there, it's going to be big, but it is going to be so small by comparison to what 3x to the fifth, the leading term, is going to contribute, that it's inconsequential, or as x gets larger and larger, increasingly inconsequential, essentially approaching nothing. And so now there's two ways to figure this out. You could say, okay, first of all, kind of direct substitute in. What happens to 3 huge to the fifth as huge gets huger and huger? It gets huger and huger and huger, right? Yeah. So you can't plug in infinity per se. Infinity is not a number, but essentially 3 infinity to the fifth is infinity, okay? So the answer to this question would be infinity, and that would be the multiple choice answer. What would also be an acceptable free response answer? DNE would be an acceptable free response answer, okay? So that one increases without bound. The other way to do this is you can look at what's called the end behavior model. The end behavior model, okay? So if we look at this quintic with all of the terms, with the positive leading coefficient, we already know that as we go to the right, it's going to go up forever. Every polynomial of odd degree, whether it's cubic, quintic, seventh degree, they come in and go out opposite sides. Now, being a fifth degree polynomial, it's going to have up to 5x intercepts and 4 local extrema. So it could look something like this, possibly. Right? You count them, there's 1, 2, 3, there's 4 local extrema. That's the maximum it can have. This is the stuff that we're saying is the local behavior, right? Look how exciting that is, right? It's like being on the river in New Braunfels in the summer. Very exciting, right? Drunk people swinging at cops and flipping tubes, right? Yeah, exciting local behavior. But if you were to zoom out, let's say that is the river, and these are like people that are getting arrested, okay? If you're like floating over the river and you zoomed out further and further and further, you would no longer see the local behavior, right? This would get smaller and smaller, and all you would see is what? You would just see the end behavior. Yeah, it would look something like this, and it would kind of do something, and then it would do that. That's all you'd see if you zoomed out into outer space. And here's where you would want to zoom in then to see what's happening on the river. And so we call that the end behavior model. It's the function 3x to the fifth. And you can use that by itself without the leading terms. It's kind of like the parent function. You can use that to determine the end behaviors. So because the end behavior model increases without bound as x goes to infinity, so does the function itself, right? And as you go out to the left, of course, for what it's worth, that's this one. We got the limit now as x goes to negative infinity. Again, you can kind of do it by the end behavior model. It's going to be negative infinity. Or, for the most part, again, this is how we're going to do it. You get rid of everything that's not the leading term because it does contribute, but pretty insignificant for huge negative values. Now just kind of plug in a negative value. What do you get when you plug in a negative number there? 3 negative to the fifth is what? Negative. So the magnitude is going to get really, 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 really big, but the sign is always going to be negative. So that goes to negative infinity. All right, so we have an infinite limit at infinity. And again, that's not a vertical asymptote because it's not at a specific value of x. So that would be the multiple choice answer. And of course, a safe free response answer would be D and E. Okay, but those again aren't the most interesting types of end behavior limits because, they don't taper off. So let's get to something like this. The cool thing is when you read the limit and you see infinity, you can start like doing Uber analysis. You don't have to think about local behavior. You're just looking at what's happening to this thing for huger and huger values. So if you want to use direct substitution, because e to the negative x is continuous everywhere, that's your exponential decay function. Remember, let's review very quickly. If you take the e to the x function, which is monotonic increasing, what does replacing x with negative x do to any function, including this? Reflects it across the y-axis, yeah. Your x's are trading places. Positive and negative x's are switching. So that would be the graph of, that would be the graph of e to the negative x. So again, if you know what the function looks like, you can answer this question very quickly just by either envisioning the graph or looking at the graph. What would the answer be? Hop on the graph, head out to the right. What are we getting closer and closer to? 0, right? Is approaching the x-axis, which is y equals 0. So that's the answer. But how could we do that maybe if we didn't know what the graph is? Direct substitution. I would do this off to the side. E to the negative infinity. Again, if you write e to the negative infinity or e to the infinity, people that are math purists are going to freak out. They're like, oh, you're plugging in something that's not a number. Okay? Because really it's a limit. But we understand what that means. So you can simplify that, put it over 1, and now you can get rid of the negative exponent by bringing it to the bottom. 1 over e to the infinity. And so now the denominator is exploding. It's getting really, really, really big, really, really fast. And the numerator is always staying a 1. So what's happening to your ratios? When the denominator gets bigger faster than the numerator, they get smaller and smaller and smaller, approaching 0. So that's the kind of analysis that we are able to do with infinity or negative infinity that we can't necessarily do with numbers, right? Because we're just looking at general trends for unfathomably huge values of x. Yeah, for what it's worth, what would this one be? What would be the limit as x goes to negative infinity, the left-hand behavior? Well, again, if you knew what the graph looked like, it's the green one, and my lines are kind of shaky. But as we head out to the left, where are the y values going? Yeah, they're going up to infinity. So again, if you know what the graph looks like, you could say infinity or D and E. But again, you can kind of use direct substitution. If you plug in, you get e to the negative infinity, which is the same now as e to the positive infinity. So that's basically powers and powers of essentially 3, right? And that's getting really, really big, really, really fast. Okay, so that's the analysis we can do. Now, exponential functions are really, really cool because they do have end behaviors that are quite dramatically opposite. On one end, depending on if it's a growth or decay, you're going to have an infinite or a negative infinite limit. And on the other side, you're going to have a finite limit, a horizontal asymptote at some y value. So dramatically different results. Whereas quintics, right, they don't have dramatically different results. They're both infinite on both sides. Or if you had a parent function like x squared, it would be infinite on both sides. But exponentials, pretty exciting. Okay? All right, let's look at this one. The limit as x goes to infinity of sine of x. Again, we kind of talked about it up above. If you think about the graph of sine of x, you go out forever, you're oscillating between two fixed values, 1, -1, 1, -1, 1, -1. So it's not infinity, right, because it's not increasing without bound. It's not negative infinity. It's not decreasing without bound. It's not tapering off to a finite y value. What can we say? If it's oscillating between two fixed values, we would say D and E. Yeah, there is no limit. It could be literally any number between -1 and 1 if you go out far enough and take a pulse, but then you keep going, and it continues to bounce between -1 and 1. So this would be D and E by oscillation. So remember, limits can fail to exist for many different reasons. This one would be D and E by oscillation. It's not an oscillation discontinuity, as we saw the other day, but it's D and E. The end behavior limit is D and E by oscillation. Now, it gets kind of interesting when we take that function and we add a little something to it. like an X in the front, okay? If you were to use direct substitution and you plugged in, you would get negative infinity times sine of negative infinity. And that really doesn't make sense, right? Because you kind of have something that's approaching negative infinity times something that doesn't exist. If you have something that's infinite times something that doesn't exist, what do you think the answer is? It's kind of hard. So let's think about this graphically. Do you remember what the thing in front of the sine function affected on the graph of sine? Like the amplitude. Good. We have a lunch right now. All right. So that X will affect the amplitude, and we'll see what it does after lunch.